so I don't leave it in that state. Oh, you're ready, okay. All right, so Prasanth, do you want to
Yeah, can you hear me?
I can definitely hear you, that's good. And
Okay.
we see your shared screen. In fact, it's just the right aspect ratio.
Yeah, okay, I'll go. Okay, my name is Prasanth. I'm a graduate student at the University of Florida, and I want to talk about a package, a new event selection tool that we've put out. So this is the ThickBrick tutorial, and it's based on this paper that came out last year called Optimal Event Selection and Categorization in High Energy Physics. And to run the tutorial, you need the ThickBrick package and these requirements. So we'll get to importing ThickBrick in a second, and we'll look at what ThickBrick does and so on in a second. But first, these are just the inputs that are needed to plot stuff, just basic NumPy and so on. So what is ThickBrick? It is an event selection and categorization technique. So at the analysis level, you have some data that's passed your triggers and so on, and you have, say, some high dimensional objects, and you're going to construct some event variable, perform an analysis, but you want to perform some event selection. Or you might want to categorize them and say, here are my really high purity events, and this is the second tier of events and so on. So you split them into a bunch of categories and you analyze them. And ThickBrick is both a technique and an implementation of the technique to perform this category, this selection and categorization. It's actually a three-part series of papers, out of which only one has come out. And the first part is focusing on signal discovery. So in order to get the best sensitivity for a discovery analysis, the prescription for event selection is given in part one. Part two deals with parameter measurement, and part three, which will hopefully come out sometime this year or early next year, is reducing systematic uncertainties in our analyses using event selection. But in this talk, I'm not going to focus on that. So we're just going to stick to part one. So what does part one do? Essentially, it sets thresholds on machine learning based classifier outputs. So you train a BDT or a neural network to classify between signal and background, and that gives you some output, say a number between 0 and 1. And then once you've done this pre-processing, you use ThickBrick to set the selection thresholds or the categorization thresholds. So the goal of this talk is to try and convince you that ThickBrick is worth doing it. Like, what's the big deal about setting a few cutoffs, right? So instead of getting into the theory of things, I'm going to focus on a physics example and just elaborate what ThickBrick does with this one example. The background and the signal under consideration are resonant decays of ZZ versus ZH, and the signature is the Z goes to mu plus mu minus, and the other Z or the other H goes to dV bar, right? But just for the sake of argument, let's just for the sake of this presentation, let's make it harder. Let's set the mass of the Higgs to be 100 GeV. So you're moving the Higgs peak closer to the Z peak. And I'm also setting a rather high jet PT resolution of 25, right? And we're going to scale down the signal cross section to about 3 signal events per 100 background events. And this, used as a familiar proxy, does not belong there. Never mind. So what our data set has 100,000 background and signal events, but in the histograms that we plot, we're going to scale down the signal events to be about 3 per 100. So how under the data files folder over here, we have the MATLAB banners if you're interested in them, and then we convert the LHC files into LHCO files. These are unsmeared, and then we just manually take all the beat jets and apply, just smear their PTs with a resolution of 25%, and those are stored here. But okay, what do we do with this data? The analysis goal is to look for the Higgs in the data, and just to be clear, this is just a proxy for a typical physics analysis. It can be, you could be looking for BSM search analyses, you could be looking for event topologies with missing energies, in which case your analysis variable is not going to be just the invariant mass of the digits, but it can also be, say, MT2 or MBL. So insert appropriate event variable here, right? So in this case, however, the discovery variable is the digit invariant mass. And this is what the histogram looks like. The blue part is the background, and you have some signal on top of that. And if we just normalize each individually, this is what it looks like. So we can see that the Z peak, the Higgs peak is actually closer here. And this is a difficult problem, right? You can't just, and it really depends on how many events went into this to know if we can actually detect this signal over the error bars or not. So that's where event selection cuts come in. So what's the goal of event selection cuts? To make our data signal rich. Now, if you just look at this right, the histogram on the right, one easy way of increasing the purity of the signal here is to say, let me just place a cut on my event variable itself. I'll just place a cut here. Everywhere, the bins to the right have more signal and the bins to the left have less signal. But that alone is not going to improve our analysis. Why not? Why doesn't it improve it? Well, placing a cut here is going to increase our S squared over B. But that is relevant when you're performing a counting experiment. For a shape analysis experiment, what's relevant is that is the sum over all each bin of this quantity S squared over B, and it can be S squared over N, or it can be other complicated forms. But I'm just going to use this particular form as a proxy for this talk, right? So when you're doing a shape analysis, what matters is this form right here. And once we made this distinction, it's clear why setting a cut on MJG is not going to help, because all that can do is throw away some bins from the summation, and throwing away some bins is not going to increase this number, right? Because this is positive by construction, right? Uh, so then how do we perform event selection? We all know this. We need to cut the background from below. And how do we do that? We need to use the information that is complementary to the event variable. And these are the variables that are not plotted here. So you look at data within a given, within a bin in MJ or within some region, and you ask, how are the other features of these events distributed, and what makes them more signal rich or more background rich? And we need to cut on those complementary and on that complementary information. So one of the popular thing now for the last few years is using machine learning based classifiers. So we do that, we train a neural network, and that is actually stored here. So that's the notebook that trains the neural networks, and its outputs are all, the trained neural network is saved here, and the data from the neural network, meaning the output that it returns, is also saved under data files. So we're not going into those during this presentation, but the end result is that this is the distribution of the neural network outputs for my signal events and the background events. So so far so good. So what do we do with this neural network output? We place selection cuts. So we can say, let me place a cut here and only select events beyond, say, 0.2, 0.2 or 0.5 or 0.9. And that's the effect of these histograms show the distribution post event selection. So I apply a selection cut of 0.05, and this is what we get. Now it might seem like it's not doing much, but only 28% of the background passed the cut of 0.5, whereas 80% of the signals survive. And if you increase the cut, if you make the cut stronger, there's an even higher thing. And a question to ask is, okay, where is the ideal cut? What's the cut I need to place in order to get the best sensitivity? But before we address that question, something to note is that our invariant mass is highly correlated with, P is the neural network output, by the way. So, and P stands for the probability of an event being a signal event, given its features, right? So the point is, the invariant mass is highly correlated with B, because of course my signal is going to be peaked around the 110 mark, but whereas our background is going to be peaked away from it. So it is something that the machine is going to learn. And we originally said that cutting based on MJJ is not going to help. And in the case you're throwing away bins, it could even be bad, right? So then how do you control the neural network from learning from MJJ? There are some techniques like preparing your data in such a way that only information complementary to MJJ survives, but that's kind of difficult. We saw a technique earlier in the morning where you resample them so that you smooth out the distribution and so on. And I will connect what ThickBrick does to that approach later in the talk, but let's address the problem head on, right? There is a correlation between these two. Let's just plot that correlation and see what's going on. So this is my invariant mass, and this is my neural network output. I'm using the logit function just to see the spread in the p-values more clearly. And this kind of shows us the problem clearly, right? If we place a nominal cut, a horizontal cut, and say these are the events above this line are going to be selected, you can see that that cut is too strict for the bins on the left to pick up the few signal events that are out here. And it's too lenient for the bins on the right to kill the background here and improve the purity there, right? So the issue comes in because of our flat cut. And then our idea is make the best out of each bin, right? Choose a different cut at different values of the invariant mass to maximize the S square over B in each bin. Or if you want to perform an unbinned unbinned analysis, then you can say maximize it at each value of MJJ, right? And one of the things that we prove in the paper is that across all event selectors out there, you have you can take your features, say it's 10-dimensional features or 6-dimensional features, and there's an infinite class of event selectors that you can define on this, which are the events that will be accepted, which will be rejected, right? Out of all of those, the best one can be gotten in this form, where you just learn P and set an appropriate threshold in P as a function of MJJ. That will pick out the best, the optimal event selector, hence the title of the paper, right? Now that's all good, but now our task moved from finding one good threshold to finding a threshold function of the invariant mass. So that's just more work, right? And this is where ThickBrick comes in. And so this is the first time I'm importing ThickBrick. I import ThickBrick as TAAB, tab. And we'll talk more about what this kernel regression is, but ThickBrick comes with a built-in one-dimensional kernel regression, which I'll use later on in this talk, right? So what does ThickBrick do? What are its inputs? The inputs are just the invariant mass and the corresponding piece. It doesn't care about anything else because, what was that? I just got this. I looked at the question that popped up and I got distracted. Anyway, the corresponding. So yeah, ThickBrick doesn't care about what the event features are, how many features went into the neural network, which events are signal, which events are background. ThickBrick relies on the neural network to process all that information and give it this one number P that says, based on my training data, this is the probability that an event is signal given its features. So it relies on that and it takes that for granted, right? And so in my data preparation, I'm just going to take my signal and the background data sets, and I'm just going to randomly permute them. I don't need anything else, right? So that's fine. What are the, you need to make some choices in using ThickBrick, and the choices are pretty straightforward. Category count, the number of selected categories. So this, so you could have, for example, in this form, I've allowed event rejection, and I've said there's one selected category, and that's your typical event selector, where events are either in or out, right? Or I could turn off my allow rejection, and I can just say there are two categories, and I'm not going to throw away any events. I'm just going to analyze them separately. So split them into two. So these are these are two choices. Initialization mode, ThickBrick is going to come up with this optimal distribution, optimal thresholds using an iterative process. And when you start off an iterative process, you need to give an initialization mode. And all in one category just means that right at the start, it's going to say everything goes into category 0 or everything goes into category 1 or something. And after that, it will split them into, it'll split the events into different categories. So, but the initialization mode is not a huge deal. It's not much of a choice, right? And finally, we come to the statistical distance that you want to maximize. So you have 6 different choices for it. And this is what the choices look like. So let's just pick this one guy, Pearson chi-squared. This is what we've been looking at, right? Except we've converted the summation over, so X stands for the event variable. In this case, the invariant mass of the digits. And we've converted the summation to an integration. So we'll be doing things in an unbinned fashion. So what is this summation over C? That is when you have more than one selected category. If you have, say, 3 selected categories, you'll sum over each category and sum over each bin in X, and you'll calculate this. And these other measures may be familiar. That's just S squared over N. And these are more precise formulas for setting the significance of annexes and so on. So all of these, they just capture how distinguishable our two hypotheses are. One being there's no background, there's no signal, and the other being there is signal in my data, right? So you just pick one to maximize. So just these 4 choices. And now comes the usage, and this is the part where we get into the tutorial aspect of the talk. And just to be clear, the widgets are not part of the package itself. That's just some presentation gravy using IPy widgets, but you can just set them like you normally would with any Python argument, function argument. So step 1, you initialize an autocategorizer object. And so you just say, these are the, I need so many selected counts. I'm allowing event rejection, and this is the statistical distance to maximize. And again, I will get back to what this kernel regression does, but make a note that there is some regression thing that's going on here, right? So step 1, you specify, you give your specifications. Step 2, you set the training data, and recall that the training data does not contain any information about which is background, which is signal. It just knows what the distribution of this P is for different values of M, basically, right? You initialize the categorizer, and this just sets, in the way we've chosen, it just initializes all of them to the same category, and then it does this iterative procedure. And the ThickBrick part, the tutorial part is just this AutoCAD.training step. You just call that, and it'll perform one training step. And this is really fast. And I've not run any of these. I just pre-ran the whole thing, but I'm just going to show you how fast this can go. This is processing about 200,000 events. So, and it takes about a second per training step to deal with 1 million events for the original paper. Now that slows down if you have more categories in your, if you're selecting it into multiple categories and so on. But overall, it's not terribly, it's pretty fast, right? So you train this categorizer iteratively. Great, you've trained it. What do you do with the train categorizer? You get a snapshot of the train categorizer by calling this function, get the current categorizer, right? And if you want to perform future training steps, this snapshot that you stored will not be affected, which is nice for plotting purposes. For example, after each of these training steps, you can take a snapshot and you can say, okay, well, let me see how it progressed and what exactly it did. So it's good for visualization purposes. But before we get to the visualization, what does this categorizer do? What can I do with it? It can categorize, right? So I can call cat.categorize, 100 being the invariant mass and 0.9 being the P. And I print it and it says 0. So what do these outputs mean? -1 is the rejected category, and 0 through count -1 are the selected categories in increasing order of purity. So in the case that we're dealing with right now, there's only 2 options, -1 and 0. So when you give it 0.6, it's saying reject that event. But when you give it 0.9, it says accept it. It doesn't have, you don't have to call it individually one event at a time. You can pass an entire array of events and it will return all of those, right? But there is some boundary where this flip happened. At some point between 0.6 and 0.9, it said that's above this particular threshold, you select these events. So how do you get the boundaries? You just say cat.boundaries of 100, or you can also pass an array of invariant mass values, and it'll give you the corresponding boundaries of those invariant mass values. Note that your output is a list here. Now, why is it a list? That's because you can have multiple. So in this case, there's only one boundary, the boundary between rejection and selection. But when you have 5 categories, there's the boundary between rejection and the category 0, boundary between 0 and 1, and so on. And so it'll return a list of boundaries for each mass point, right? So then let's just plot the boundary, and all of this is just matplotlib. And the only part that matters is that I call the boundaries on this uh, uh, X is just some array that runs from 50 to 175. I get the boundaries for each of those and I just plot them, right? And this is the threshold that it's finding. It's saying pick points above this, select points above this into your analysis, and you will have ended up getting the highest S squared OB in each of these bins. Now, the thing is, it is making the assumption that the neural network did its job right? And something to note here is this interesting flattening thing going on, and I'll comment on that later if there's time at the end, right? But what I want to do next is talk about how exactly it found this. What is the like? Let's take a peek inside, and to take a peek inside. Before doing that, let's just train it with 3 categories, because it just looks, the plots look more clear. It's easy to understand what's going on when you have more categories. So I'm going to throw in 3 categories, but something I'm doing here is in the first few steps, I am taking snapshots. I'm getting the current categorizer before finishing off my training, right? Again, it converges. And now these are the trained, these are the cutoffs between my categories. And we see that at 120, when I give it over here, it's rejected. And then when we go up to 1-ish, it's in category 0. You go up further up, category 1 and category 2. So it's kind of clear what it's doing. It's just using these as the cutoffs to move them from rejection to the first category or second, and so on, right? So under the hood, it's doing this. What's going on is a k-means clustering type thing. And I don't want to go these points. Instead, let's look at plots. I'm going to fold all of this out. So let's, I mentioned that right at the start, it's going to assign all of them in the same category. So how does this come out of it? That's more of an implementation detail. But at some point, it will come out of that lull, and it'll have 4 different categories. So this is my rejected category. This is my category 0, category 1, category 2. So let's say that's the start of my iteration. From here, how do I proceed? How does this step proceed? It first computes the mean P within each category. So it's going to say over here, pass a regression line through all these points. And that's my dotted line through the purple points. I have a dotted dashed line through the green points and dashed lines through the magenta points. And these are just finding the average p-value for the events in that category right now, in this current step, right? You can notice that there's no line passing through the gray points here. And that's because the way of making it work is to say all these rejected points have an average of 0. Meaning if an event gets thrown here, it doesn't contribute anything to it. And the math works out. So that's why you don't see dashed lines through this. So then you say, well, given these means, we need to find the next boundary, right? And the next boundary is a function of these lines. So between the dashed line through the purple category and the dashed line through the green category, based on the values of the dashed lines, you construct the next boundary. And so what does this next boundary do? You just categorize all of your events based on these new boundaries now. So you will notice that because this solid line moved up, our green band widened from where it started, right? And this is a single iteration step. And the idea is to run this until you don't have too many reassignments. So in each iteration step, some points get reassigned, and at some point you won't have any more reassignments, or the number of reassignments will be really small, and that's when it converges. And this is the convergence. This is the converged boundaries, right? And I want to scroll up for a second, and I want to show this huge output that it plotted. So what is it printing out here? The first part is just me saying, print the training step that you're in right now. So ignore all of this. So when you call a training step, it returns uh, some what's the word? It outputs some messages to check for convergence. And right now at this stage, we're just returning how many points were reassigned. But there's some ideas to add some more information here to for people to use to test for convergence and so on, right? But moving forward, all this is nice, but how do they perform, right? So this is the original event selector that we trained. Using this, are we seeing any improvements? In order to test that, let's get the best flat cut as well. And you can notice that I'm using this evaluator class that is also from ThickBrick. And I'll talk about that in a second, but essentially I'm defining functional categorizers that just says if P is above a certain value of the cut, accept it, else reject it. And I'm using my evaluator to evaluate different categorizers with different cutoffs, and I'm picking the best one, basically. So that's how I get this best flat cut threshold. And this is what it looks like. So I use my ThickBrick selector, and I compare it against the best flat threshold selector, and they perform similarly. And this is something I'll comment on at the end again if we have some time. They seem to be performing similarly over here, but when you get past this 100, it's saying instead of having such a strict threshold, I'm going to become more lenient in order to extract as much sensitivity as I can from each of the bins to my left, right, to the left. And something you can also notice is that despite looking very similar over here, it has a much poorer background efficiency and a much poorer, it lets more background through, right? Uh, and in this way, it kind of deviates from traditional event selection goals, which is to kill as much background as possible and get the best square over B. But those goals are not aligned with the goals of the analysis perfectly. And you can look at this as a way of removing that misalignment, right? And finally, we just do a histogram and say, let's get this S square over B in each of these bins for the best flat cut and for ThickBrick. And you can notice that over here, they're performing similarly, but ThickBrick manages to extract a lot more sensitivity from the bins to the left, right? Now, what are some other features in ThickBrick? This tutorial doesn't cover everything that happens in there. Uh, oh, yeah, okay. One is the evaluator class. Just like it's very similar to auto categorizer, except you're not going to initialize anything, and there's no training, and there's no getting categorizers and so on. More like you tell the evaluator how many classes, how many selected categories are you allowing event rejection? What is the statistical distance? For example, you can train with one, and you can evaluate under a different statistical distance to see what's going on. And then you just give it different selectors and say, how is it performing? So the way to look at it is ThickBrick by itself is a machine learning technique, although it's piggybacking off of neural networks. It's machine learning in its own right. And so you use the auto categorizer for the training and the evaluator for testing and validation, right? And another feature that I didn't talk about is that when we are dealing with this form, S square over B, just transforming just scaling the signal up or down does not affect the optimal categorizer. So if I have a selector that gets me the best S square over B, summed over all bins, it is going to give me the best S square over B even when I scale the signal up or down. But that does not hold for other distances. And so if you want to specify, because our training data is not going to have the same, is not going to have a representative signal cross section. If you want to scale down the signal, you can just specify that at the training step. And the reason we're putting it in this training step is because the cuts that ThickBrick will give you can be directly applied on your inputs, neural network, the output from the neural network. So it's all handled internally. There's no, like, you don't have to worry about the scaling part. You just say, assume that the signal, there's only 3% signal than what I gave you, and just find the appropriate cuts for that. But give me the cuts in a form that can be applied directly on my inputs, right? So you just go from event, pass through neural network, pass through ThickBrick, and you know whether or not to include it, right? And something else I didn't put in this list is the one-dimensional kernel regression. And where does that come in? We perform this regression, right? Finding the average p-value at each value of mj. That you need to use some form of some form of regression for that. One option is kernel regression, but you can also use functional curve fits and so on. And the way we implement it here is we do have one built-in. It's pretty fast, but we have one built-in kernel regression implementation, and there is plans for including a two-dimensional KDE as well. But we set it up in a way that you can use other publicly available libraries, write wrappers around them, and just pass it here. Because here, this stuff is a callable. Kernel regression.nw, Nadaraya Watson kernel regression. It's a callable, which takes data and then returns another callable that you can call to get the average value at different points. So this is just how typical kernel regression libraries work. So you can write wrappers around your favorite fitting function. For example, we had a talk yesterday with zfit or zfit. So you can write wrappers around that and just incorporate the functionality here. We didn't want to tie this to a particular package out there because then the development will have to like follow closely with what they're doing. But instead, we provide this.
Prasanth, I'm holding up the 5-minute sign.
Okay.
And you want to use those 5 minutes for questions, I think. Yeah.
That's actually all that I have. The last bit is moving forward. We want to write up the papers for part 2, which is for parameter measurement, and part 3, which is reducing systematics, and incorporate that functionality into this package. But something else that I want to mention is that we'll be happy to help out. So yeah, we'll be happy to help out with the adoption of the technique in a real analysis or a test study, just because, again, as I mentioned, this is machine learning in its own right. So the way it works is not so much you run it and you get the appropriate result the first time you run it. It's more, it might take an afternoon to make the whole thing work with your data, for example, right? So we'll be very happy to help with that. And also the package ThickBrick does a single job, right? It's highly focused. It's not, there's no plans of expanding it. On the contrary, we'll be happy to incorporate the implementation into a larger package if that makes it easier for adoption. So we'd be happy to help out with that as well. And yeah, with that, I'll take questions.
Thank you.
So yeah, thanks very much. I've sent you the presenter view of the questions. So could you just share those while
Actually,
Jim,
second.
If you share those, then Jim can basically be the moderator and just step through them, highlighting them.
How about this? Does this work? Do you see the questions?
Yeah, but those are kind of the small ones. If you go to the Zoom chat, I sent you a private link to the presenter view.
Okay, my bad.
I'm typing in that if it helps you find it.
No, I found it. Yeah.
Okay.
There we go.
Great. Yeah.
Okay. All right. So I've got the thing way zoomed in here. So first question, this sounds an awful lot like training. This sounds an awful lot like training a boundary classifier. So like a support vector machine over the space of a neural network output and MJJ. If that's the case, what's the advantage of ThickBrick over simply adding an SVM step to the neural network and train them together?
I don't see the SPM connection immediately, but I do see a connection with kernel regression, for example, which is very similar to SPM. So in that sense, I do get this. Then the question becomes, what's the objective that is being optimized by the SVM step? If that's similar, then yes. I'm not sure if they're going to be equivalent. Now, something I did not have time to get into is that in principle, what ThickBrick gives you is the guarantee that no matter what the distribution of your data is in MJJ, you will have the exact same classifier. It did not quite come through in the plots for a particular reason, but the point is that it'll remove all shaping. So it's not saying if my input data was flat in background and flat in signal, then I won't have any shaping. What it's saying is I can bias my data in any form I want. I can change my signal shape in MJJ in any form I want, and so which will affect the neural network outputs, because if you have lesser signal, the P in that region is going to go down, and it will affect the corresponding outputs that ThickBrick finds on those values. But the combination, the physical selector that is represented by the two, is going to be unchanged by the distribution, regardless of what the distribution is. And I'm not sure if an SPM step would give you that kind of a guarantee. Now, granted, that guarantee is in principle, and what it's contingent on is that the neural network is trained well, and it's trained, and you can trust the value of P to be good, and so on. So you may have to perform some recalibration, but after performing the recalibration, the ThickBrick gives you that guarantee in principle. Right? And I'm not sure the SPM will do that, but I will look more. I'll look into what the SPM step is, and I'll be happy to talk on Slack about what exactly is the SPM step you're referring to.
Yeah, and if the original person who asked this question wants to join on Slack, then go ahead. Let's move on right now to the next question. So what are your thoughts about combining this with a fully differential analysis, like the ideas presented on previous days?
With the fully differentiable analysis ideas.
Yeah, to make the whole analysis differentiable, so that even things like the cut is something that there is a derivative, and you can derivative.
That would be possible.
Yeah, or if I can interject before your answer real quick, just to add some clarifying stuff. Yeah, how would the optimization, or how would the optimization in ThickBrick adapt to having access essentially to the full input data instead of some expert level information like what you're getting right now? And then the follow-up question to that is, what if the number of categories for the optimal number of categories for the data that you're looking at could be learned?
Okay, so this actually is an excellent question. So a couple of things. One is, what is the optimal number of categories? Well, there's two competing things, right? So if you increase the number of categories by construction of the formulas that we had earlier, your performance has to increase. And asymptotically, as you have infinitely many categories, you'll get all the information contained in the true data, because essentially you're killing any form of mixing, right?
Yeah, you're going back to an unbin fit, basically. Yeah.
But what we notice here in the paper is that the returns for increasing the number of categories diminishes very fast. So with 5 categories in the example that we considered there, we start saturating the performance. And so the real question of like how many categories should I have comes down to how much data do you have, right? Because if you start splitting your data too fine, then you may not be able to validate your Monte Carlo and so on. So these practical considerations will dictate how exactly you're going to what's the word? How exactly you're going to pick the number of categories. And the other part of that, which was, instead of dealing with some higher level variables, how would ThickBrick perform with the entire data that's coming in, like a much larger?
Or let's say you have some learnable feature engineering between the input data and ThickBrick.
Yeah. So the way ThickBrick was originally conceived was to kill the neural network in the middle. Just say I have some event, say captured by E, and I want to just output the classes that it needs to go into. These are ejected, this goes into 1, 2, 0, and so on, right? And so it did both at the same time. It said, and so you just need to construct appropriate loss functions that do both, where it learns P and learns to categorize them, right, in one step without splitting them. But we kind of ditched that because that was just going to make it a lot harder to adopt, because people are already doing neural networks. We didn't want to ask them to like stop what they're doing and do this other cost function, which is iterative and so on. So
yeah, that's completely reasonable. Yeah.
Yeah.
Rather than getting deeper into this, this sounds like it should go onto the Slack.
Yeah, I was about to do the same thing and try to cut it off. I think it would be, or if you weren't following it already, it would be interesting to go through the presentations that were shown before and try to understand how that intersects with ThickBrick, because I think there's actually the potential for quite some improvement in existing analysis based on that. So we'll go to the next question.
So next question, how do you assign input if you need to deal with combinatorial background? Is this a clear question?
No, I get this. So I would say that different combinations of your final state particles, right, they're also part of your feature set in some sense, because I have an event and I don't know which muon to pair with which bjet, say. Mm-hmm. And let's say my strategy is to combine both, take all forms of categorization. Then technically, the background is going to have both combinations. Background events will have both combinations, and the signal events will have both combinations. Now, from that point of view, it's clear how to deal with it. Now, I haven't really thought about thinking of the wrong combination as a background by itself, right? Mm-hmm. Instead of just treating it as part of your feature set. So I don't know which would be the right way to look at that question, but I would think that for the sake of like classifying as between a number between 0 and 1, what I described earlier would be the way to go, which is you treat both the right and the wrong combinations as being part of the input feature of your events.
Okay.
Because so the neural network inputs should be things that we can construct out of our visible data in our detectors. So it should be reconstructed jets, and then if we don't know what the right combination is, then we have to put in both, right? Or apply some cuts, pick the better looking combination and so on. But yeah, that's how I would deal with combinatorial background.
Mm-hmm. Okay, thanks. One final question. You want to click through?
It's not, yeah. Can consider systematic uncertainties.
Yeah. So I'll say it. None of the distance metrics you showed consider systematic uncertainties, which can be more important for many analyses. Systematics more important than statistics. Can you adapt this in some way? And how crazy would it be to integrate a full likelihood model?
So I didn't mention that part 3 was going to do systematics, and this is the plan to do that, right? In part 2, we're going to kind of question our analysis, our event selection strategy completely for parameter measurement analyses, which is if you're trying to measure the mass of the top quark, right? It doesn't matter if an event is more like, it does matter to some extent, whether an event is more like a TT bar event or more like a pair produced W event, because one depends on the top mass, the other one doesn't. But the more relevant question is, because we're not trying to look for the top but measure its mass, the more relevant question there is, given an event, is the density in that region going to go up as we increase the top mass, or going to go down or stay same? Because if we have some part of the phase space that is unaffected by the mass of the top, then even if it's signal, it's useless to me, right? So we kind of switch the input from switch the supervisory signal to the neural network from saying these are signal and these are background to saying these are affected, these are not affected, or these are affected to this extent. Here counts go up, counts go down, and so on. And from that, you're going to get the best categorization for parameter measurement. And how do you do that? You say, accept the events that are most sensitive to the value of top mass, right? And part 3 is going, again, there's going to be math that proves all of these things, but part 3 just switches that the other way around and says, let me do that with my nuisance parameters. And then I'm going to select events that are, or I'm going to reject events that are sensitive to the value of nuisance parameters. And that is kind of how we are going to propose to kill systematics. But yes, for the first part of the question, the distance measures of this paper are not relevant to that at all. Although it does help with systematics a little bit by killing background shaping. The focus is not killing the systematics. That will be in part 3, and yes, it can be done. And how crazy would it be to integrate a full likelihood model? Full likelihood model will be perfect, because the paper that we wrote did not deal with neural networks. That was a toy example where we said, I'm going to use my knowledge of these events to take an event and calculate its cross-section, differential cross-section under signal and differential cross-section under background, and just take the ratio, right? That is my P, which ThickBrick dealt with. Now, if we have a full likelihood model and we're willing to perform the computational, if we're willing to use the resources to get those computations right, ThickBrick will be more than happy to take the output from those models to perform just a categorization. I don't know if that answers the question.
Maybe I could ask, you're referring to part 3. Is that in the notebook on Indica that people can look at offline?
Parts 2 and 3 are future papers.
Oh, okay.
And yeah, they're not, it's not, hopefully for next PyHEP.
Okay.
Hopefully at the next PyHEP, we'll have a technique to reduce systematics with event selection.
Okay. All right, well, thank you. Any other questions from the audience? Otherwise,